All right, let's take a look at section 4.9, which is on a very, very important topic called antiderivatives. And we're going to use this a lot throughout the rest of this course. If you go into Calc 2 for your major or minor, then you will see this again and again and again. This is kind of like the other half of the course. We spent all that time talking about derivatives and applications. Now we're going to look at antiderivatives. And all of this relates to each other and is all tied together in the end. So make sure your cell phones are put away and you're taking good notes as we go through the next couple of examples. Suppose you're asked to find a function capital F whose derivative is 3x squared. So what I want you to think about is kind of working backwards here. If the function is 3x squared and I want to go backwards and say what function has this as its derivative, what would it be? So think about it. If I take the derivative of this, I get 3x squared. Well, hopefully you're thinking x to the third power, right? And if you're not, that's okay. Think through it now. If I gave you that and said take the derivative, you would tell me 3x squared. So that means that capital F is the antiderivative of that function. That's what we call that. It's kind of like thinking backwards or working backwards. A function capital F is an antiderivative of little f if f prime, sorry for all the f's, big F prime is equal to little f. In other words, if little f is the derivative of the capital F. Can a function have more than one antiderivative? So for example, we know that the derivative of x to the third is 3x squared, but what about x to the third plus 5? That would be the same derivative, wouldn't it? What if it was x to the third minus 17? Same thing. The derivative, because that constant would just zero out, would be the same derivative, 3x squared. So if capital F is an antiderivative of little f, and capital G is an antiderivative if and only if. All right, a lot of notation, a lot of words here. Let's get to it. This is called the general antiderivative. So here's where I'm headed with this. When you take the antiderivative, so in that last example we said x cubed was the antiderivative, you're going to put that plus c on the end of it, and that's called the constant of integration. So what that means is adding any constant to the end of it would have the same derivative as having nothing there at all. And you'll see what I mean. We'll do some practice with this. So let's do an example. Number 1 says find what's called the general solution to this differential equation. All that means is you have an equation with a derivative in it. So dy dx is equal to 2x. So what we can do here is we can say, all right, we're working backwards. The solution that would be in the form y equals what function has 2x as its derivative? Well, that would be x squared, right? Think about that. The derivative of x squared would be 2x. And then don't forget the plus c, because adding a constant, any constant to that, will have the same derivative. A more common way of writing the solution to this differential equation, or a differential equation like this, is to use what's called an integral symbol. And we'll get more into this notation later on, but right now, what I want you to do is recognize that when you see this integration symbol or anti-differentiation symbol, it's the same thing, it's the same directions. So a few rules here that you need to be familiar with, just like when we first learned derivatives. These are the same analogous rules going in the other direction. The integral of 0, the dx is just notation, and it means with respect to x. So that's all that means is notation, with respect to x. So the integral of 0 would just be a constant c, which should make sense because the derivative constant would be 0. The antiderivative of k with respect to x would be kx plus c. So for example, if I said, what's the antiderivative of 3 dx? You would tell me it's 3x plus c, because the derivative of 3x would be 3, and that's it. If you have a constant multiple, so this one is called the constant multiple rule, that says if we're multiplying by a constant, we can move the constant to the front of the integrand, just like when we did derivatives, and then just carry on with integrating the rest of it. This rule, I don't know if there's a name for it, adding and subtracting rule, I guess. But basically it says if you're adding and subtracting terms and you want to integrate that or find the antiderivative, you just go down the line, term by term, just like we did when we took derivatives. The last rule here is called the power rule. And this is probably the most important one that we're going to do today. This is the analogous rule when we first learned derivatives, the power rule. So x to the n, so if n is a constant, the integral of x to the n with respect to x will be x to the n plus 1 all over n plus 1, and then plus c. So for example, if I had the integral of x to the third power, power rule says n is the 3, and so it would be x to the 3 plus 1 all over 3 plus 1, which would be x to the 4th over 4 plus c, and that's your power rule. So let's look at some examples here. Oh, a couple more rules for the trig functions. So these are your rules for your trig functions. The antiderivative cosine is just sine x plus c. The antiderivative sine x is going to be negative cosine x plus c. The antiderivative for secant squared x is tan x plus c, and the antiderivative for secant x tan x is secant x plus c. These should make sense if you think about what is the derivative. For example, what is the derivative of tangent? That's secant squared x. So the antiderivative secant squared x would be tangent x, going in the other direction. The antiderivative cosecant squared x is negative cotangent x plus c. And the antiderivative for cosecant cotangent x is negative cosecant x plus c. And I will provide these for you, but you need to get to where you can recognize them when you see them. All right, find the antiderivative or the indefinite integral, that's another name for it, check it by taking the derivative. We can always check our work by doing the derivative in the opposite direction. So letter A, I have x to the first power and 2. 2 is a constant. So I can look at these separately and just go down the line. X to the first power, using my power rule right here, it's going to be x to the 2 plus 1 over 2 plus 1. Plus, now 2 is a constant, so I'm going to use the constant rule right here. K would be kx, so this will be 2x. And then plus c, and I'm going to go ahead and clean that up a little bit. I get x to the third over 3 plus 2x plus c, and that's my antiderivative. I'm going to skip the check for now. We'll do some of that in class. Let's do the next one. 2 sine x, so according to the rules above it, the antiderivative sine is negative cosine. So it's going to be negative 2 cosine x, constant multiple, you just do 2 times the integral of the rest of it. 3 cosine x, the antiderivative for cosine is sine, so plus 3 sine x, and then minus x to the 5th, that's my power rule again, so that's x to the 6th over 6. So I'm going to rewrite this so I can fit my c in there. And then minus x to the 6th over 6, and then plus c. And there's my antiderivative. Letter C, I've got 1 over x to the third power, so I'm going to rewrite that first, just like when I took derivatives. If you see this and you're asked to take the derivative, you need to rewrite it so that you can apply the power rule. Same rule applies for antiderivatives. So I'm going to rewrite this as the integral of x to the negative third dx. Now apply the power rule. It's going to be x to the negative third plus 1 over negative 3 plus 1. And then I'm going to simplify that as x to the negative second over negative 2 plus c. You can leave the answer like this, or if you don't like that negative exponent, let's move it back to the denominator, and that would be cleaned up a little bit more. Last example, we've got the square root of x. So just like when we learned derivatives, we have to rewrite this. Remember, this is an implied 2 and an implied 1. This is x to the 1/2 dx. So now apply your power rule. So you have x to the 1/2 plus 1 over 1/2 plus 1. And that gives me x to the 3/2 over 3/2. Get a common denominator, 2 over 2, you get 3/2. And when you have a fraction like this, remember that dividing by 3/2 is the same as multiplying by 2/3. So I'm going to multiply by the reciprocal 2/3, and that goes away. So that leaves me with what? Looking a little bit cleaner, I get 2/3 x to the 3/2 power and then plus c. And that's my antiderivative. So when you have a complex fraction like that, I do want you to go ahead and clean that up using the reciprocal rule.